All right, so I'll give you, what I want with this talk is to just give you a brief idea of some ongoing work that I'm doing on developing some static analysis for data scientists. So these data scientists are these people that, well, they're not quite computer scientists, they're not quite mathematicians. They have some specific domain knowledge, so they put all of this together. And what they do is that they write code, even if they're not professional software developers. So what they write code about is to make sense of data. So there's data that essentially surrounds us, and it's used to make decisions about us. So the code that these non-professional people write ultimately has an impact on our lives. So it decides if we get hired, if we get a loan, and can drive our car and all of this. So essentially, when they write software, obviously, when you have at the moment you start writing code, you're going to have some bugs in the code, whether you want it or not. And so and the problem with this data science code is that the bugs are not just, they don't just make your code crash suddenly, but they can be a little more insidious. So there can be bugs that make your code work anyway, give you a result anyway, but you don't really realize that something went wrong until maybe much later, if at all. So this was a technical mistake that was made, but it was an example of data processing that went wrong. So it was in the UK. They had collected COVID cases and put them in some CSV file. And this was then opened in Excel. And somehow, because of some formatting reason, some of the data went missing. So a lot of the cases went unreported, so the contact tracing was not done. And so a lot of people were not warned there were contact cases for COVID. And so nobody noticed that this went wrong until, well, much later. So this kind of bugs are a bit of a problem. And so one of the technical instruments that data scientists use are these Jupyter notebooks. So these are files in which you can write text, you can write cells of code, you can do visualizations and all that, and this is all done in some interactive setting. And so this is often done in prototyping. So when they want to make sense of some new data that they get, they explore the data with this. But in several cases, actually, this Jupyter notebooks in several companies, these are actually used in production as well. So it's not just a prototyping tool. So it's used for making sense of real data, and using the results of this code is used for real things. And so we want to make sure that, since this has an impact on us, we want to make sure this code works. And the interesting bit here is that, well, most of the problem, this has stopped. Yes, most of the problem with this code, actually, well, this was in the XKCD comic a few slides ago, but most of the bugs in this code come from data that is unexpected. So the code is written with some expectations on the data that it's supposed to take, but then something changes at some point. So maybe the source where you get the data from gets updated. So now they send different kind of data, different format of the data. They add columns, add fields to the data. They had information. They remove some information that you were using. So now suddenly your code breaks because, well, the expectation that it had on the code doesn't make sense anymore. And so we could test the code, and as a matter of fact, this code is actually rarely tested. And the problem with testing is that it's actually hard to test for these things because one needs to be aware of the expectation that it has on the data. And so it's not that simple to do. And so that is the motivation really for doing static analysis for this. So the idea is also that it's not that costly anymore, not hard anymore to do static analysis, so we can also do it for this kind of code. And the main idea of this is that, well, so we have our Jupyter Notebook, our code, and behind it there is the data that is, this code is reading. And this is sort of in a black box, so we don't know what data we're getting. I mean, the person writing the code knows, but is not necessarily explicitly aware of the expectation it has on the data. So what we want to do with this analysis is sort of open this black box in which we have the input data and sort of reconstruct the expectations that one has on this data. So to make things a little more concrete, we can maybe focus on a simpler format of data, so CSV files. These are essentially tabular data. They are organized in columns. These columns are fields, and you have various rows of data. And even with this simpler form of the data, it's already a first challenge for developing some static analysis that tries to reconstruct this data or the shape of this data, the expectation on this data, because it's a data structure and it's multidimensional data structure. So we're going to work with this and try to build some static analysis, some based on abstract interpretation. And so what I like to do to describe the way this is done is sort of in 3 steps, this recipe of 3 steps. So the first step is to define a mathematical model of what we want to prove, of what this program is doing, which is what we call the concrete semantics usually. Then we build, on top of this, we build the actual static analysis, so the abstract domains, the abstractions, the approximations that we do, and then we actually have to make this implemented in practice. So I'll just give you a brief hint of all of these things without formulas or anything, just some intuition. So starting from the concrete semantics, so the typical concrete semantics is the trace semantics. You have the executions of the program. So the difference in this case is that, well, the execution depends on the input data, depends on what we're reading from the input. So in a sense, what the concrete semantics is doing is essentially putting more and more constraints on the input files that can be accepted by this program, that can work with this program. So we start with all possible input files, if you want, all possible CSV files, and then the more we execute the program, the fewer files are okay, the fewer files satisfy our expectations. So we sort of restrict the possibilities that we have. So it's sort of, well, for those that know this, it's sort of like playing Wordle. You have all possible words at first, and then you put more and more constraints the more you play. And this is another challenge in doing static analysis for this, because you have to do some indirect reasoning. It's not just about the values of the program at this point, a certain point in the code, but it's what they mean in terms of the input that the program is reading some time ago. So there is, this indirect reasoning about what its statement in the program has impact, how this impacts the input files that the program is reading. Okay, then, on top of this model of concrete semantics, we can build some static analysis, so a very simple one. It's really maybe we want to reconstruct what columns we expect, what fields we expect our data to have. And so this is a very simple static analysis. It's really just sets of names, if you want. But in practice, it can get quite challenging. Well, I mean, the first things are easy. So at the moment I'm putting snippets of Python code. I mean, you don't have to read all the details, but the idea here, we just read a file. So we know that there is a file somewhere. We don't know nothing about this for now. If we access some column, then we know that this file must have this column, obvious thing. We also have some dependency here, so we are creating a new variable out of this selection. So we are making a selection of a data frame. So we are creating a tabular data structure to represent the data, and we are selecting part of it and storing it in some other variable. So we have some extra dependency that we keep track of. And then later on, we figure out that on this new variable, we're actually doing some operation. And so we are assigning some column named profit with the result of the computation made on 2 other columns. And so this tells us, for instance, that We do have the two columns that we are using to compute. So we have sell prices. We knew that before. We have buy price because we are using it in the operation. And we are writing this into this profit column. And this profit column may be a newly added column. So it could be that this column didn't exist before. So we are adding it now. Or it was already there and we are overwriting. So the result is that we may have this profit column and all the other ones are columns that we must have. And this is all simple code, but then the moment you start doing actual real data manipulation, you have much more complicated things. You may pivot tables, you may group by things, you may do some grouping operations, selection operations, and so on. So the analysis gets a little much more complicated. Maybe the column names are not strings, but they're expressed as results of some variable which comes from other operations and so on. So it can get quite messy. And of course, the dependencies that you have to keep track of can get sophisticated. And this is even for just a very simple analysis like tracking column names. So the moment you have to deal with these languages, most of the time Jupyter notebooks have Python code in them. You're going to have to deal with complex library calls. And so then of course combined with the fact that we're dealing with data structures, it makes it all fun, but also complicated. So one thing that we can do about this is to make the analysis more practical. So the idea is to, instead of reporting everything that we can possibly know about the files, maybe we would just want to give the essential information to a data scientist, something they can actually use directly as it is. So for instance, instead of reporting which columns may be in a file, we may want to just tell them what columns are definitely going to be in this file. So then essentially giving them necessary expectations. So expectations that if they are violated, they're definitely going to have some problem. So since I may know the question coming, I know about this paper. So it's essentially going in the same direction, so same idea, except that we're dealing with not input to functions, but really data files coming from the outside. So complex data structure files. But the ideas are essentially the same. Okay, then in terms of the implementation, this is really, at this point, it's mostly a wish list of the implementation. But so to make it work in practice, one thing to do is, in these notebooks, you have cells of code that you can run in different order, in a sense. So, and you can write the code and execute it while you're writing the file. So what you want is the analysis to make it to be useful is to be interactive. The moment you change the order of executions, you want to adapt your static analysis results. So that means, keeping track of results that you had and maybe updating them up to a certain point and so on. Then, as I mentioned, most of the time we're using Python code in these notebooks, but sometimes it actually also works for R, for instance. So and sometimes there is Python and R together in the same notebook, so we have to support multiple languages. And then, one thing that I'm also looking at now with a student is some sort of combination. So we're dealing with dynamic languages here, so that's, a lot of this is hard. And so one thing that can help is have some sort of combination with the static and dynamic analysis. And so an idea is to use some executions use static analysis to figure out which executions we need to see next to sort of cover the whole program, or at least most of the program. Wish list, really. So that's pretty much it. I think I have sticking to the time. Happy to take questions, comments, remarks. Thanks.
Okay, we have time for a couple of questions from the audience.
Yeah, I took away the question from Francesco.
Francesco?
No.
Or maybe Patrick? Yeah?
So it's a general question because people make errors in the way they handle data.
Yeah.
You make a static analysis, but you finally ask them to validate in the last step. And so if it is the same people, they will do the same errors. And so I am missing something here.
Yeah, so the way we want, I should have mentioned it, but one way to use this is to maybe make some automatic checking of, so the result that you get is essentially what the program expects from the data, or vice versa. Given this data, what the program should do. And so what you could do is take this result and make some checker that automatically checks new data that comes in before it's fed to the program. Or, if you have data and the program and there is a mismatch between the two, then you may want to either fix the code or fix the data. So basically guide them in this, in this space. Yeah.
Okay, any other question from the audience? Okay, so let's thank again the Caterina, the speaker.